a little bit more faster with a very minute hit on the model accuracy. But for now, for this purpose of this demo, we are just going with the floating point model. So just click on download the model. It'll convert the model and download the model. So for our convenience, I have already trained this model and downloaded the model. What you get is basically an unquantized model because it has been no quantization. It's floating point 32, and you get a labels.txt file as well. What does the labels.txt file look like? It basically contains the labels that you trained your model with, along with the indices. Next step is basically just to create a sample Flutter app and actually just drag and drop these the model file as well as the labels file into our Flutter app under the assets folder. So here what I have done is I have already created a sample Flutter app. What we did was whatever model we just trained, we have dragged and dropped our labels.txt and the model TFLite file right here. Now, in terms of the Flutter code, there is nothing crazy going on here. It's just like loading up our normal model and then calling the splash screen. Splash screen is basically our initial screen that you see on the load up of any app. So that is basically that. So I'm just using a library here for doing that. You can provide a title. This splash screen is not important for the TFLite. It's just basically saying that, okay, show that for 2 seconds, and after that move to the main home screen, and then we go to the home screen. So this is where all the magic is happening in terms of inference on the app. So what I do here is basically I set up some variables. First variable that I set is basically a boolean, which actually tells me that the model has the model done loading or not. So you have to load the model in order to do the inference. Second thing is basically the image that you are trying to do the inference on. And the third variable is basically the outputs. So how TFLite gives output in Flutter is basically in form of a list of dictionaries. And that list of dictionaries has certain number of 3 basic things. It has the label, it has the percentage accuracy, and it has the index of the label from the text file. So these are the 3 keys for which the model generates the values. And these are the 3 keys of that dictionary which are in this list. So we have this list here. So where do we start from? So to start from, what we do is basically create a classify image function. In this function, what we do is basically we call a TFLite .run model on image, because we are going to run the image classification on an image that we are going to provide. If you are using image binary or something else like segmentation or something, then this thing might change, like run model on binary or something like that. Next, you provide the path to the image. Then you provide the number of labels that you're expecting from the model as the output. So basically here we have cats and dogs. So 2 is the number. In terms of threshold is basically that above what kind of percentage of accuracy do you want the results to be displayed or to be outputted. I'm setting it to 0.5. You can set it to 0.9, 0.8, depending upon your model performance. The image mean and standard deviation come from the MobileNet original code function. So if you see that whenever you train a model, you actually pre-process the input. In terms of MobileNet version 2 or version 3, what you can see is that if you go to the code of MobileNet, you will see there is a pre-process input function that is being called. If you look under that pre-process function, you will see that the images are being normalized by 127.5, which is basically 255 by 2. Why we do this is basically to normalize the images so that they are on the same scale. So doing this brings the images to the scale of between the scale of -1 to 1, with 127.5 as being like the center point. So after that, what we do is we set the output that we get from this model to our global output, and we set the loading to the false because our model is done loading. One important thing why we are using here, defining this as an asynchronous function and using await here is because any kind of TensorFlow model or any other model that you're using or any other operation that you're doing is basically, if it's going to take some time as compared to for like making inference or doing some kind of things, you don't want to block the rest of the operations that are going to be there. For example, if you're playing music and then suddenly you are running a model or something, you don't want the other things to stop and wait for the model to finish and after that continue with that. So that's why you provide define this as an asynchronous function so that this can run in parallel. While we are waiting for getting the output from the TensorFlow model, we are still running things like, for example, refreshing the screen or running things like that. So we basically wait for the TensorFlow to give its output and then display the output. So that's about this. Then we basically have a load model function where we again use that as an asynchronous function depending upon how big your model is. And then we load the model and we just provide the path to the model, which is under assets and then model unquant .tflite. And then we also provide the labels.txt file. So once we are done with this, what we say is that whenever this home screen is called in the initial state, we just load the model during that itself and just provide the value. So this is basically all the model classification and TensorFlow model loading, classification, and outputting code that you need. One important thing is that once we are done with the classification and all the things, make sure to close the TensorFlow model. This basically helps you avoid memory leaks and dispose of the function once you are done using that particular model. Rest of the functions are basically helper functions, which are used for picking images, basically like choosing the image that you want to use for classification. Or if you want to like basically use a camera, and if you want to use images that you have stored on the phone, you can use the gallery. Ignoring most of this code, which is more like a wrapper function for doing things. This is the main thing. You just print out or like show your text as output, and then you put your labels. So remember, I told you that the output is basically of a type list, which has a dictionary inside that, which has 3 keys. So in those keys, you can actually see that you go for the output, and in the output, the dictionaries are basically in the descending order. So you take the first dictionary out of that, and from that you get the label key and the value corresponding to that label key. So that is your predicted label. So this is what gets printed. So if we now run this application, go to run and debug. I'll be running this on a Pixel 3 XL, but if you want to try it on iOS and you have Xcode, you can do that as well. Or you can have any other device. You can connect your own mobile phone as well and try this out. So let's launch this. Okay, the app is built and it's installed. The APK is installed. Now the app loads. Remember the splash screen. This is the splash screen, and this is our home. So now remember, we defined 2 functions. One to select the images from the camera, which is like you can take a picture, or you can use the images that are stored on your phone. I'm going to use the images stored on the phone. So go here, select an image, and click on select. And it predicts that it's a dog. Let's try it out for a cat. And these are the images that were downloaded from Google. So these are not in the training set or test set. So it predicts that as a cat. Awesome. So with this, we come to end of the part 1 of the presentation. Let's move on to part 2. So this part is done. Now the second part. So that was more beginner friendly, and don't worry if you didn't get everything. All the code for Flutter app and all the other things with instructions are provided in a GitHub repository, and all the links are in this presentation. So you can definitely go back and check everything out. Next thing that we are going to make is basically EuroSat land cover classification Flutter application. So what is EuroSat land cover classification dataset? It's basically a dataset that has been taken from the Sentinel-2 satellite that roams over the Europe. and they have selected a lot of different countries and tried to figure out that what are the areas to keep a track of things. For example, like agricultural land, things like lands that have annual crop, lands that have a permanent crop, like a fruit orchards or vineyards, or like there's a pasture land which is used for grazing of animals. Then there are built up areas, highways, residential, industrial buildings, water bodies like rivers and sea lakes and things like that. So why is this data set important, or why this problem is important, is because you want to keep a track of how things are changing, how the land cover is changing, whether there was land previously and now that land is being used, so there is less amount of forest or things like that. So you want to keep a track of those things. So an example is basically like, for example, in the left image, if you see, earlier in 2015, the parts under the green, in the green boxes, were basically kind of a forest area or were more green. And now later on, if you see, they have become a part of the farming or the land area. Similarly, if you see, this area was underdeveloped and there were not many buildings. And after 2016, there you can see a lot of buildings there. So you can actually keep a track of how the things are changing and how the forests are reducing, or how the land use is increasing, and classify those things. So for this project, the steps would be like, this is more like beginner to intermediate friendly. So in this, we'll be taking the second path for deploying a model. We'll be training a machine learning model. We'll be training the machine learning model by ourselves using TensorFlow 2, and then we'll be saving the model, converting the model to TensorFlow-Lite format, and then using that in the Flutter application. So all the dataset and the Colab notebooks are available, so you can take a look at that. Okay. Cool. So let's go.
We just have a question here. Let me just take a question here. So there's a question that how do you deal with noisy image? That is, specifically, do we need to train with different model? So if an image is noisy, do we need to train it with a different model, or we can just denoise it within this model itself?
So there are a couple of options. The first option is basically to train your model with the noisy images, depending upon your application. If at the end where you are going to deploy your model, you know that you are going to get the noisy image every time, then maybe you should just take that as the ground truth data and training data, and actually train your model on that. And hopefully the model will be able to figure out that what that data is about and how that makes sense. The second option could be, you could add a pre-processing step before sending your images into the model, which could be like denoising the images. Like you could use an autoencoder or like a super resolution model to improve the resolution of the images and things like that.
Awesome. I think that it answered the question. Carry on, please.
Cool. So in this, basically, what we'll do is basically we load the dataset using TensorFlow datasets library, and then we load the EuroSat dataset. EuroSat has two types of dataset. One is RGB images, and second is basically banded images, which are basically like different kind of bands in which the satellite picks up the images. So here we are going to use the RGB images, and I have already split that into train, validation, and test sets, and a basic some information about the images, that what number of features are there and how the images are. So if you see, the image is basically of type 64 by 64 by 3, so it's a pretty small image. And the labels are basically like, we have 10 classes, and these are the labels which are of type TF64, and the images are uint8. So here are some of the images that you can see. So a sea or a lake is basically defined, and an image is something like this. A forest cover looks something like this. The highway, if you can see this is the highway, looks something like this. An industrial setting would be something like this. A residential setting would be like a bit more dense as compared to an industrial setting. The rivers look like this, or like this. So what we do here is we just define the number of epochs, and we are loading a pre-trained model. So we are using here a MobileNet V3 small model. You can change this model and use any other model that you like. For example, ResNet model, SqueezeNet model, or any other model that you like. So what we're doing here is basically we'll be training it for 50 epochs with a batch size of 64. We are just keeping a buffer for pre-fetching the images so that our GPU is never running empty. We always are feeding the images constantly so that our GPU, we have a better GPU utilization. And then I'm setting the images size to 224 by 224 for input for mobile net, but you can change it according to your model needs. And we know the number of classes is 10. These are some just pre-processing functions where we are performing data augmentation, like flipping the image left, right, horizontally, vertically, changing the brightness, saturation, contrast, and things like that. And then we are also normalizing the image as we go in and resizing the image to the shape that we require. And we are normalizing with the same values to keep it between -1 to 1. Next, you just pre-process the images. You just run through all the images in parallel uh, and pre-process all the images for the train, validation, and test set. And then you have a train, validation, test set, which you can shuffle with the buffer size, and then you can pre-batch them so that you are prefetching the images and you can cache them locally. So that makes the things a bit more easier. Now you can see like what the images look like after the augmentation. So basically we create the model, we use the MobileNet v3 small model as it is, and we don't use the top layers. We remove those top fully connected layers and things like that, so that because we want to provide our custom number of classes. And we use a pre-trained model, which was trained with the ImageNet. So we are loading the ImageNet weights here. Setting freezing all the layers so to false, setting them to false, adding the global average pooling, and a dense layer, flatten layer, and defining a number of output classes, that is 10. And then basically using the model, compiling the model, we are using stochastic gradient descent here as an optimizer, and sparse categorical cross entropy for the loss. And we'll be using the metrics as accuracy as the metric. So we just create the model, and this is the big model. So basically creating a learning rate scheduler here, early stopping, looking at the validation loss and early stopping if the model is not performing well or the validation loss is not changing after a certain number of iterations. And then we are also keeping a checkpoint for the best model that was there with the depending upon the validation loss, and just training in the model. So this is all the train logs. If you can see, the validation accuracy looks kind of good. Then we save the model. In order to convert this model into TFLite, this would be the preferred way to save the model, which is like saving the model using tf.saved model in that format. But if you want to use like save the model as a Keras model, you can save it like this as well. Now here we are just testing the model on the test data set, and we see that accuracy is kind of 0.968, which is good. And then we just plot the confusion metrics just to see how well the model is performing. So we can see at one point of time, it took one image of highway and thought that it was an annual crop, and similarly happened with the permanent crop, but otherwise most of the images looks pretty good. So you can just see the predictions. So you can see here that it says the true prediction was a highway, and it thought that it's a permanent crop because most of the area is pretty green and you can barely see the highway going through that. So maybe that was the reason that it got confused. But otherwise, in most of the other things, whereas it's residential or sea, lake, and things like that, it works pretty fine. Now, the main step is to convert the model into a TFLite format. To convert a model into a TFLite format, there are 3 to 4 different options for model optimization. One is that you save it using just the converter as a test, and you don't provide any other parameters. So you'll get a floating point 32 TFLite model. So this is basically the code. We are using the saved model that we use from tf.saved model that we saved here. If you want to use the model that you saved using Keras, you can save from Keras model and then provide the path to that. So we use the TensorFlow converter and convert the model, and then we save the model in a TFLite format. Similarly, if you are want to optimize it for size or optimize it for latency or optimize for both, you can provide the parameters in optimizations that what kind of optimization you want, and you can save that. So this basically provides a dynamic range, basically creates a dynamic range a TFLite model, which takes is of type int8, but during inference it can take in the int8 option and then convert to floating point 32 to perform inference. And similarly, you can use tf.float16 to have your model in the floating point 16 type. So that the advantage of using floating point 32 and 16 is basically that you can the TensorFlow GPU delegates are currently supported on floating point 16 and 32 because the GPUs can work well with those and not with int8s. So that is the benefit if you are using this kind of format. Then we'll just compare the size of the model. So you can see the floating point original model was around 8.5 megabytes. Floating point 32 is basically 7.8 megabytes. Floating point 16 is almost half than 32, and similar for the int8. So while we see a good decrease in the model size, so depending upon where you are deploying this, you want to also see the model accuracy, how that is getting affected. So this is just a helper function that takes in the model and adds a batch size dimension to the TFLite model for doing the inference. Then you just take a test data set and you invoke the interpreter. You set the input tensors, set the image to the input tensors, you invoke the interpreter, and then you make a prediction. And once you have the prediction, then you can just print that out. So testing it for floating point 32, you can see the accuracy is pretty good. And the inference time is pretty small, like 0.87 seconds and things like that. So it's pretty good. Same for floating point 16 and int8. And then you can just save your model. And that's it. So now going towards creating the Flutter app for this, you will see the app actually looks pretty similar. The step number one is basically downloading the TFLite models that you generated from that notebook and putting them right here. One thing that you don't get from that process is basically the labels.txt file, but you can create that by yourself, which is basically putting all the labels in the same order that you trained your model on. So once you are done, the main file is still the same. The splash screen is still the same. Only thing that changes is here. All the functions remain the same. Loading the TensorFlow model, classifying with the model remains the same. Only change is right here, which is you have to provide the path of the new model that you're going to use. And that's it. No other changes are required. It's basically just the same app that you can use and change your models. So let's run this and see how this looks like.
Meanwhile, let me make a quick announcement. Everyone, please do fill in the feedback form to let us know what more would you like from us and how you like this session. And if you have any questions, do drop it in the chat box. Thank you.
Okay, so the app is up and running. And again, it's the same format. You just click on the camera roll. You can allow for permissions. Let's see. So I took how I got these images for doing this inference for this demo is basically I went to Google Maps and actually search around places around Chandigarh and other kind of places that would kind of match the data set and try to figure out that how the model performs on that. So this is basically a crop of the small part of Sukna Lake from the top using Google Maps. So let's see, what does it say? It says it's a sea or a lake, which is correct. Next, it's the Ambala Chandigarh highway. Let's see how it predicts that. It says it's a highway, so that looks good. Similarly, we can take other kind of images like maybe this annual crop. So this is its annual crop, so definitely looks good. Awesome. So with this, we are at the end of the demo. So I would like to share some resources. So all the Jupyter notebook and the Colab notebook that was there that I showed you, plus all the Flutter apps, both the Flutter apps that I showed you along with the TFLite models pre-trained are available at this link. See, so these are some other resources. Definitely check out Teachable Machines for making a lot of models. You can not only create TensorFlow-Lite models, you can create TensorFlow models, quantized models, even models for TensorFlow JS, or even Google Coral boards. And then do check out the TensorFlow Lite tutorials for a lot of new things that are there in terms of model optimization. There are a lot of other things that you can use, which is model pruning, basically pruning the different layers of the model in terms of like standardized pruning or layer by layer pruning. Or you can look at like weight fusion and things like that for making a model size small. So do check out that. And this is basically a talk from this year's Google I/O that talks about what's new in the TFLite converter. So do check out that for in-depth about how TFLite converter works at the backend if you're interested. Also, a good learning point around TFLite would be the deep learning.ai TensorFlow data and deployment specialization, especially the course 2. And if you want to learn a bit more about why we use async and await in Flutter, or even it's the same concept in the JavaScript as well, if you're from that world, so you can definitely check this out as well. With that, thank you, and I can take any questions.